Well, thanks very much. Thanks for the invitation to talk here. I should say that this is a longer talk. Some of you have heard it before, and I apologize. And I also apologize it's not yet completely written up. My collaborators and inspirers are on the list. I should expect the title probably in two ways. When I first went to Caltech in '76, I worked in the Kellogg Radiation Laboratory, where breakfast cereal was even more famous than nuclear synthesis, and Snap, Crackle, and Pop were the marketing device used for selling Rice Krispies, and it turned out to be a bit of a metaphor for what I'm talking about. I should say also that what I'm talking about is, it would be pretty clear, is heterodox, if not and probably rather controversial. It's a very different way of thinking about and looking at what might be possible around black holes. And I do this in the spirit of presenting alternatives as target for observations, rather than the total conviction that the many models that have been simulated are essentially on the right, are not on the right track. So I mean, I do offer this in the spirit of offering alternatives. So let me go straight on. You've had all this. I'm sorry I wasn't able to join you yesterday, but you know most of this. Let me just emphasize 2 points that I think are observation. I say my approach to these things is very different from most of the theorists working in this business. It's not sort of reductionist, it's rather inferential from observations. And so for me, the things that are points that are pretty clear are that the rotational energy of a pinning black hole is enough to keep the Virgo cluster going in M87 for a trillion years. The jets are perhaps 100 times more powerful than anything we see from the disks and the inflows, and the mass supply rates are almost certainly orders of magnitude larger than what is accreting onto the black hole. Also true for Sagittarius star. Many more to said in the many observations, which you probably will go, but there's still a lot we don't quite understand. So here are some motivating questions. Why the disk and the sort of plunging region so dim compared with the power of the jets? The second is, what drives the mass supplied away? And there's clearly, I think, it has to be an outflow, and I'm going to claim it's essentially all of it, but it needs power to do that. The third is, the jets are observed to be collimated at perhaps 10,000 gravitational radii. And a sort of long-standing one going back to the '60s is that the powerful jets, including M87, are associated with elliptical galaxies. Those are questions. This is, in order to make this work, the fields that I'm talking about are significantly larger than those that appear in most of the simulations, and this is driven essentially by what my radioastronomical colleagues infer to be the power of the jet. So you heard all this in a very nice talk from Elliot. I won't go through all this again. This is the sort of essentially the paradigm, the modern paradigm, now called a magnetically arrested accretion disk. And you've seen lots and lots of simulations of this, and it may well turn out to be right. But I'm going in a different direction. This says, there's a thick iron pressure supported torus and continuous flow. You don't get any respect in this business unless you have an acronym. And so this one is whole energized magnetically mediated ejection disk. And basically the point is that everything is powered by the spin of the hole. Basically these are cartoons, not simulations, of course. On the very largest scale, it's the quasi-spherical inflow that provides the ultimate collimation of the jets in these and other galaxies. And so that's why they happen in ellipticals, not spirals. The gas that falls inwards, much more supplied than actually accretes, very little accretes, and it's all blown away by power that's carried out through the disk by torques applied at its inner edge, and so it's an ejection disk, not an accretion disk. And there's a large MHD wind, as complicated as the solar, probably more complicated than the solar wind, and that is ultimately responsible for the sheaths that are observed that are collimating the jets. The transfer of energy from the spinning black hole to the inner part of the disk is mediated by two generic mechanisms, and again, these are only cartoon level. One we call a clutch, which is sort of instabilities and so on, and the other we call sort of excuse me, it's called Gargamel, and that essentially is a magnetic connection between the ejection disk and instabilities that carry things out. It was a capstan is the other word I was searching for, sorry. And that's basically a magnetic loop attached to the disk, non-axisymmetric, and then is caught by the black hole. All of this sends power outwards through the disk, and accretion power is irrelevant in the extreme case. The accretion power in these sources is irrelevant as it is in the sun. Okay, because there's another source of power there. And so if we go on, so it's essentially powered by rotational gravitational energy. And my focus has been very much, and my colleagues, is on global conservation laws and not building up from microphysical models. So here's one point I'd like to make here is that this really is much of this is very distinguishable observationally, particularly in polarization. The sort of standard view is something like what Parfrey et al. Did in beautiful simulations where you have gas flowing inwards, a current sheet in the equatorial plane close to the black hole. All of this is in principle observable through polarization. In our view, the magnetic field lines, except very close to the horizon, go straight through the equatorial plane, and what happens is those field lines fall back until E is of order B. Then there's a magnetic turbulence that's caused. That puts a whole lot of electromagnetic energy onto Penrose orbits going backwards onto the hole, and so you're extracting energy not from just the horizon of the black hole, but also from the ergosphere outside it. And then, of course, there's more energy that comes from the ejection disk. So this is, quite distinguishable, I suppose. This is kind of silly. I won't go on. Okay, all right. So let's go to snap, crackle, and pop. So basically, with the strong magnetic fields, it's a very different sort of emission mechanism. The snap is if you get impulsive acceleration in magnetically dominated regions, and rather than looking at some sort of steady growing, which is very different from the sort of models that Elliott described. The emission is essentially from a lot of fast flares locally, and you may not be able to distinguish them individually, but there'll be radiative and expansion cooling associated with this, and strong polarization signals. I would say for the emission mechanism, of course, there's been many acres of prose written about relativistic reconnection, all highly important and relevant. Another possibility is what I call magnetoluminescence, which is that as a result of reconnection, the magnetic flux tubes organized, shown schematically down as the rope, organize themselves essentially into slip knots. And it's a very topologically, they're sort of unknots, if you like, and they can resolve at the speed of light rather than a tenth of the speed of light. And so could be very potent accelerators. I tried to get some simulators to simulate this, and they were very enthusiastic, and then went off and solved a totally different problem. So that happens. So if anybody will do this, I'd be thrilled to work with them, or just watch them do it, because I think this is an interesting process to consider. Okay, the crackle. Basically, there are two types, as I think one would think about. One is flares, which one might naively associate with the equatorial plane, particularly with the sheath as it gets close to the black hole that separates the jet from the outflow. And then also there'll be very short sparks and so on associated with the jet itself. And key thing about these features is that the cooling goes as T to the cooling will be asymmetric. And you can search for this in existing data that sits in ALMA, looking for three-point correlation functions and so on. And this will be a way of seeing there's any time arrow in the total flux that's already measured. And also you can do this in frequency cross correlation, because flares should cool as they go. That gives you a cross correlation, which again you can seek statistically. So there's that, and so we've got some ideas about how to look for that. Say a little bit about geometrical optics here. Again, the way my colleagues look at optics, I mean, everything that's done with ray tracing is all good and fine, and we've heard lots of didactic discussions of this. The way I do this is rather different. Obviously, everybody here has been exposed to all of this, but the slightly different way of doing this is to imagine a wavefront going backwards from the observer towards the source. Follow that single, originally expanding spherical wavefront. It wraps itself around the black hole, shown sort of schematically here. And that wavefront is essentially has a phase associated with it, which is essentially just the Bohr-Lindquist time, and its gradient obviously is the k vector, and all you have to do is for a given spin, and in fact you can generalize over spins, but let's just take a given spin of the black hole, you once and for all trace these wavefronts, and then on the wavefronts you can code the Hessian or the inverse magnification tensor, you can code the time delay, obviously, you can code the polarization rotation, which is the only thing you need to know. And so just asking in a potential source region what the wavefront is there, then you can get the get what you will see on the sky. It also tells you, of course, where it appears on the sky. If you want to use this for interferometry, as you do, and so you can see, obviously, interpret the photon sphere and the Einstein and the ring, photon ring on with a radius of about 5, and all of this material, all of this optical information is encoded once in the wavefront. You calculate it once and for all, and then you could be inquisitive about different potential source regions. So this is an alternative way, and it's very fast, and you can do it on a laptop and so on. Okay. The crackle is essentially obviously echoes. Many people have pointed to this. You can think about the rays. A generic ray its magnification will change sign as you cross a caustic, and so you can segment the individual rays if you like, or equivalently the wavefronts. You can just segment them, and so you can see obviously lots and lots of images, but you're mostly interested in at most 2, and usually only 1. And again, this is a very simple way of looking at the echoes that you can see from close to a black hole. And I'm just trying to see how much time. Yeah, okay, we're doing okay. The other thing is to say, and I've just should have shown this schematically here, is that if you think of just about a Schwarzschild black hole, then there's essentially a line focus or a line caustic behind it, just on the opposite side from the observer. But if you make it a Kerr black hole, that unfolds into something with an asteroid cross section that's shown schematically here. And Kevin Rauch, part of Kevin Rauch's thesis from '94, was sort of mapping these things out. And in the case of M87, the size of the caustic is typically about an AU across. It's not small, and of course, when a spark associated with the jet, the 10 exavolts of voltage there, these things should be sparking all the time. Should be highly unstable and sparking all the time. 10 exavolts is a lot. And so if a spark crosses the caustic, as it can do, then you'll see distinctive features, and they're worth looking for in the data. You may not find them. Maybe this is totally the wrong representation, but it's worth looking for in existing data. So essentially, as you cross this caustic, you'll see some, as you can see, I think it must be in the next one. You'll see 4 images, and then you'll see a very distinctive pattern. I think it's in the next slide. Here we are, yes. In the next slide, your very distinctive pattern in the flux that should be, again, already said. You can look for these things in existing ALMA data, etc. There's just total flux data. And you'll see, and then if you look at your raw visibility data with no modeling going on, just raw visibility data, you'll see an ingress. You'll get 2 images appear, and then they'll disappear on egress crossing this caustic. Again, these are occasional things that are very distinctive, and there'll be point sources that essentially run all the way around the Einstein ring on the sky. So this is a very distinctive visibility signature, and if you found 1 or 2 examples, it would be totally predictive for all other baselines. And so it's worth looking for. I think it's worth looking for these things. They'll probably be occasional, but it's worth looking, and not finding them is a very, very distinctive. So let's go on. And then I think I'm more or less finished on time, so I've raced through this very fast. Deliberately, it was more of an hour talk. So, But let's just say that obviously the HD observations are a magnificent accomplishment to us, and the MAD model is the sort of, if you like, the paradigm. It's a thick torus with hot ions and a weak field in the torus, and sort of quasi-steady emission and so on. Whereas these, if you call them HEM models and so on, have the ergomagnetosphere, which is part of the serious part of the jet production, the ejection disk, which is all the gas being driven away, and that of course has signatures that you may see from Webb, I hope one day. And then there's a magnetopause at very large radius, which is well resolved and so on. Rapid cooling is a characteristic of these models. There's the snap, crackle, and pop, which I've tried to sort of illustrate here. And I think it's worth looking for these things, and some of my colleagues have actually been trying to get hold of the ALMA data and look for this, but I'm eager for other people who know much more than I do to do this. Look at some of these signatures and see if you can find any examples of it. And yes, let's look forward to BEX. I really hope it happens, and I think we're going to discover a lot from it. Thank you very much indeed.
Thank you, Roger. That's a very exciting talk. All right, I'm going to ask my first question because I've been dying to ask you this, and then we'll let other people ask as well. So you have worked over the decades on all these different potential explanations of what powers these jets and how energy is extracted from a black hole. Do you have a favorite child amongst them, or or do you think it's all of them at the same time? Blandford's Nag, Blandford Payne, Blandford Globus. What is your best guess? There's a lot to search
I,
for here.
I'm much more an empiricist. I mean, I think these are things that can really happen and are worth looking for. And, um, we learn from, we really learn from observations. And, what you think about is constrained. There are various things that, I did a model of outflows in 1976, which was forcefully from disks and so on. Observations, I think, rule that out as an idea, but not. But it's still worth thinking about. And so I don't think there's any favorite. I mean, I was the thing I'm probably got most references is the work that I did with Roman Zayek, and that's one of the happiest collaborations of many happy collaborations I've had, because it was a sort of coming together from totally different perspectives and finishing each other's sentences almost. So it was great. So that's a favorite, if you like. Okay, I'll say that then. Yeah. Mm.
Thank you. Okay, if anyone else wants to ask questions, please. Okay, Michael.
Yeah, I'll lead off, but I'm sure others, don't be shy. So for the caustic detections of the caustics, I think that's an interesting idea. So you need these regions, the emitting regions, that have to be much less than an AU, I think you said.
Yep.
And I think this could just be studied geometrically to come up with a toy model of what it might look like on the interferometric baselines. But I just wanted to confirm. So your idea would be to look for time variability in the signal, or maybe in the interferometric response, even, not to resolve them directly, or do you have a specific idea in mind about what you think the best way to detect these would be? You mentioned ALMA.
Well, yeah, no, there are in the paper, which is still not finished, and it's probably my fault. There are at least six observational tests that could be used on existing data for the caustic crossing, which may not happen, sure, but I mean it should be a sparky region. There should be sparks. They should be being convected across the caustic. Then the two things to look for are, let's see if we go back here, are this distinctive pattern in the flux, and this is looking for these things occasionally happening in the total flux data, and I imagine ALMA's the best place to go for this. And of course, you don't want to edit out spikes. You want to go to the raw data. The last thing you want to do is to take out any spikes. And then the other thing to do is to go to the caustic crossings. You go from 2 images to 4 images to 2 images. They swing around the Einstein ring, and that can be seen in the raw visibility data. Just take any baseline, just ALMA and your favorite telescope, Sorry. Take a phototelescope, and it's a predictive signature in the visibility. And if you see it in one, say Alma and your best one, then say Alma and Greenland if you want, then it's predictive for all other baselines. So there'll be no doubt whether this is signal or noise.
Yeah.
Yeah.
So I mean, we
In the
don't
raw
have
visibility.
RFI.
Don't start. I mean, RFI is obviously a problem here, and so you're the experts. But don't start trying to model this. Just take raw visibility data, V of B.
Yeah.
I think if we look
Uh,
at the total flux and we forget about the spatial information in the image, this is going to be buried in a lot of other effects. But
Absolutely.
it would be really useful to have to understand this pattern when you do have Bex-like resolutions and you can spatially resolve the source, because these caustic pops will appear at different locations. And if we have spatial resolution, we'll get more SNR.
I'm much more interested in using existing data than, I mean, Bex will be great and obviously better, but just let me say these are, although it may look like the image on the right hand side where it says the flux as a function of time, that scale of flux, sorry, got edited out, is logarithmic. So a point source, which a spark could be, a point source is going to be very bright. And the caustics are more interesting in this context than the photon ring, which obviously obviously there's a photon ring, but crossing a photon ring is not such a big deal, but the caustic is.
yeah. Yeah. So I actually think the millimeter is a great place to look for these. There's not that many reasons that you wouldn't be able to spot it if it was there.
Even sort of setting limits is interesting, and there are two sources. I think the ones that are most likely to be smaller, but I don't really know. I mean, I can't predict the sun. I can't even explain the sun when I can observe it with Parker. So I mean, it's it seems slightly hubristic to imagine we can do all this from first principles, but the most promising is probably the sparks associated with the jet, which presumably is the thing you're most looking at. But you're far enough out, you'll see the sheath as well, and that will have somewhat larger structures, and they may be too large to make caustic responses.
Thanks.
All right, one final question from Joseph.
Hey Roger, it was a great talk. It's good to see you again. I'm really interested in the pre-computation of the lensing, so you can including the amazing efficiency boost that you get. Is there any trade-off with the efficiency that you get? Like, are you limited to the sort of source types that you can put in and solve for the photon trajectories out, or like, are you limited to viewing angle or the time scale, or is it just a completely general pre-computation that works with everything?
Well, it's quite general. I mean, basically, for a given observer inclination relative to the spin, and a given spin direction relative to the observer, say, I fill space-time with wavefronts. Now, there's more than one wavefront because they wrap around the black hole, but you segment it as you go through a caustic. You segment it, and so you can sort of organize the structure. And so along those wavefronts, you can imagine every point in space-time comes not just with a phase, it comes with a time delay, it comes with a position on the sky for when you're doing your imaging, it comes with a magnification if you were doing point sources, etc. Looking at point, and then you can involve with a finite size source for a flare, and then it comes with a polarization rotation, which is the exciting thing. And so it's an easy way to think about what we say about the ergomagnetosphere, where the field lines go horizontally through the equatorial plane rather than radially through the equatorial plane is in the more conventional models. So those are those are really rather distinctive, and you just ask, you say, well, I think there might be emission coming from this region, be it the equatorial plane or the sheath or something. what will be the observables, and the observables are encoded. Just calculate once and for all. If you say, well, I don't really know the spin, and that's almost certainly the case, then you can actually add those in as a couple of parameters and get the wavefronts then move as you go around. So yeah, I think it's quite general.
Thanks, Roger.
It's not so much computation. I mean, people can compute. It's more a question of being able to think inferentially about where the emission in the Great Orange Donut could actually originate.
Thanks.
Well, I think this is a great place to stop, and we take your message to heart that we should collect as much data as we can. And this is how we're going to figure out how these systems really work.
Well,
So
correct. Do more with the data you've already got in the can.